Chapter 8, Reactive Spring, Resilience and Scalability. This chapter covers understanding reactive programming with Reactor and Spring, building reactive servers with Spring WebFlux and Spring Data, R2DBC, building reactive clients with Web Client, improving resilience for applications with Reactor, testing reactive applications with Spring and test containers. Polar Sophia, the organization behind the Polar Bookshop business, is very happy with the progress of its new software product. Its mission is to spread knowledge and awareness about the North Pole and the Arctic, and making its book catalog available worldwide is an essential part of this. The catalog service application you built so far is a good starting point. It fulfills the requirements of browsing and managing books, and it does that while following cloud-native patterns and practices. It's self-contained and stateless. It uses a database as a backing service to store the state. It can be configured externally through environment variables or a configuration server. It respects environment parity. It's verified through the automated execution of tests as part of a deployment pipeline following continuous delivery practices. For maximum portability, it's also containerized and can be deployed to a Kubernetes cluster using native functionality like service discovery, load balancing, and replication. Another essential feature of the system is the possibility of purchasing books. In this chapter, you will start working on the order service application. This new component will interact not only with a database but also with catalog service. When you have applications extensively relying on I/O operations such as database calls or interactions with other services like HTTP request-response communications, the thread per request model used in catalog service begins to expose its technical limits. In the thread per request model, each request is bound to a thread exclusively allocated to its processing. If database or service calls are part of the processing, the thread will send out a request and then block, waiting for a response. During idle time, the resources allocated for that thread are wasted, since they cannot be used for anything else. The reactive programming paradigm solves this problem and improves scalability, resilience, and cost-effectiveness for all I/O-bound applications. Reactive applications operate asynchronously and in a non-blocking way, meaning that computational resources are used more effectively. That's a huge advantage in the cloud, since you pay for what you use. When a thread sends a call to a backing service, it will not wait idle, but it will move on to executing other operations. This eliminates the linear dependency between the number of threads and the number of concurrent requests, leading to more scalable applications. With the same amount of computational resources, reactive applications can serve more users than their non-reactive counterparts. Cloud-native applications are highly distributed systems deployed in a dynamic environment where change is a constant and failures can and will happen. What if the service is not available? What happens if the request gets lost on its way to the target service? What if the response gets lost on its way back to the caller? Can we guarantee high availability in this context? Resilience is one of the goals for moving to the cloud and one of the properties characterizing cloud-native applications. Our systems should be resilient to failures and stable enough to ensure a certain service level to their users. The integration points between services over a network are among the most critical areas for achieving a stable and resilient system for production. It's so important that Michael T. Nygaard spends a large part of his book, Release It, Design and Deploy Production-Ready Software, Pragmatic Bookshelf 2018, on the subject. This chapter will focus on building resilient, scalable, and efficient applications for the cloud using the reactive paradigm. First, I'll introduce the event loop model and the main features of reactive streams, Project Reactor, and the Spring Reactive Stack. Then you'll build a reactive order service application using Spring WebFlux and Spring Data R2DBC. Order service will interact with catalog service to check the availability of books and their details, so you'll see how to implement a reactive REST client using Spring Web Client. The integration point between the two services is a critical area that needs extra care to achieve robustness and fault tolerance. Relying on the Reactor project, you'll adopt stability patterns like retries, timeouts, and failovers. Finally, you'll write auto tests to verify the behavior of a reactive application using Spring Boot and test containers. Note: the source code for the examples in this chapter is available in the Chapter 08/08 Begin and Chapter 08/08 End folders containing the initial and final states of the project. See this link. Section 8.1. Asynchronous and non-blocking architectures with Reactor and Spring. The Reactive Manifesto, reactivemanifesto.org, describes a reactive system as responsive, resilient, elastic, and message-driven. Its mission to build loosely coupled, scalable, resilient, and cost-effective applications is fully compatible with our definition of cloud native. The new part is achieving that goal by using an asynchronous and non-blocking communication paradigm based on message passing. Before diving into building reactive applications in Spring, we'll explore the basics of reactive programming, why it matters for cloud-native applications, and how it differs from imperative programming. I'll introduce the event loop model, which overcomes the thread-per-request model's shortcomings. Then you'll learn the essential concepts of the reactive stream specification implemented by Project Reactor and the Spring Reactive Stack. Section 8.1.1. From thread-per-request to event loop. As you saw in Chapter 3, non-reactive applications allocate a thread per request. Until a response is returned, the thread will not be used for anything. That is the thread-per-request model. When the request handling involves intensive operations like I/O, the thread will block until those operations are completed. For example, if a database read is required, the thread will wait until data is returned from the database. During the waiting time, the resources allocated to the handling thread are not used efficiently. If you want to support more concurrent users, you'll have to ensure you have enough threads and resources available. In the end, this paradigm sets constraints on the application's scalability and doesn't use computational resources in the most efficient way possible. Figure 8.1 shows how it works.
Figure 8.1. In the thread-per-request model, each request is handled by a thread dedicated exclusively to its handling.
Reactive applications are more scalable and efficient by design. Handling requests in a reactive application doesn't involve allocating a given thread exclusively. Requests are fulfilled asynchronously based on events. For example, if a database read is required, the thread handling that part of the flow will not wait until data is returned from the database. Instead, a callback is registered, and whenever the information is ready, a notification is sent, and one of the available threads will execute the callback. During that time, the thread that requested the data can be used to process other requests rather than waiting idle. This paradigm, called event loop, doesn't set hard constraints on the application's scalability. It actually makes it easier to scale, since an increase in the number of concurrent requests does not strictly depend on the number of threads. As a matter of fact, a default configuration for reactive applications in Spring is to use only one thread per CPU core. With the non-blocking I/O capability and a communication paradigm based on events, reactive applications allow for more efficient utilization of computational resources. Figure 8.2 shows how it works.
Figure 8.2. In the event loop model, requests are handled by threads that don't block while waiting for an intensive operation, allowing them to process other requests in the meantime.
I wanted to briefly mention the difference between those two paradigms because it helps explain the reasoning behind reactive programming. However, you don't need to know the details of these paradigms' inner mechanics since we won't have to work at such a low level or implement an event loop. Instead, we're going to rely on convenient higher-level abstractions that will let us focus on the business logic of our applications rather than spending time handling the processing at the thread level. Scale and cost optimization are two critical reasons for moving to the cloud, so the reactive paradigm perfectly fits cloud-native applications. Scaling applications to support a workload increase becomes less demanding. By using resources more efficiently, you can save money on the computational resources offered by a cloud provider. Another reason for moving to the cloud is resilience, and reactive applications also help with that. One of the essential features of reactive applications is that they provide non-blocking backpressure, also called control flow. This means that consumers can control the amount of data they receive, which lowers the risk of producers sending more data than consumers can handle, which can cause a DOS attack, slowing the application, cascading the failure, or even leading to a total crash. The reactive paradigm is a solution to the problem of blocking I/O operations that require more threads to handle high concurrency and which may lead to slow or entirely unresponsive applications. Sometimes the paradigm is mistaken as a way to increase the speed of an application. Reactive is about improving scalability and resilience, not speed. With great powers come great troubles, though. Going reactive is an excellent choice when you expect high traffic and concurrency with fewer computational resources or in streaming scenarios. However, you should also be aware of the additional complexity introduced by such a paradigm. Besides requiring a mindset shift to think in an event-driven way, reactive applications are more challenging to debug and troubleshoot because of the asynchronous I/O. Before rushing to rewrite all your applications to make them reactive, think twice about whether that's necessary, and consider both the benefits and drawbacks. Reactive programming is not a new concept. It's been used for years. The reason for the recent success of the paradigm in the Java ecosystem is due to the reactive stream specification and its implementations, like Project Reactor, RxJava, and VertDex, which provided developers with convenient and high-level interfaces for building asynchronous and non-blocking applications without dealing with the underlying details of designing a message-driven flow. The following section will introduce Project Reactor, the reactive framework used by Spring. Section 8.1.2, Project Reactor, Reactive Streams with Mono and Flux. Reactive Spring is based on Project Reactor, a framework for building asynchronous, non-blocking applications on the JVM. Reactor is an implementation of the reactive stream specification, and it aims to provide a standard for asynchronous stream processing with non-blocking backpressure, reactivestreams.org. Conceptually, reactive streams resemble the Java Stream API in the way we use them to build data pipelines. One of the key differences is that a Java stream is pull-based. Consumers process data in an imperative and synchronous fashion. Instead, reactive streams are push-based. Consumers are notified by the producers when new data is available, so the processing happens asynchronously. Reactive streams work according to a producer-consumer paradigm. Producers are called publishers. They produce data that might be eventually available. Reactor provides two central APIs implementing the producer of T interface for objects of type T, and they are used to compose asynchronous, observable data streams, mono of T and flux of T. Mono of T represents a single asynchronous value or empty result, 0 to 1. Flux of T represents an asynchronous sequence of 0 or more items, 0 to n. In a Java stream, you would process objects like optional of customer or collection of customer. In a reactive stream, you would have mono of customer or flux of customer. The possible outcomes of a reactive stream are an empty result, a value, or an error. All of them are handled as data. When the publisher returns all the data, we say that the reactive stream has been completed successfully. Consumers are called subscribers because they subscribe to a publisher and are notified whenever new data is available. As part of the subscription, consumers can also define backpressure by informing the publisher that they can process only a certain amount of data at a time. That is a powerful feature that puts consumers in control of how much data is received, preventing them from being overwhelmed and becoming unresponsive. Reactive streams are only activated if there's a subscriber. You can build reactive streams that combine data from different sources and manipulate it using Reactor's vast collection of operators. In a Java stream, you can use a Fluent API to process data through operators like map, flatmap, or filter, each of which builds a new stream object that keeps the previous step immutable. Similarly, you can build reactive streams using a Fluent API and operators to process the data received asynchronously. Besides the standard operators available to Java streams, you can use more powerful ones to apply backpressure, handle errors, and increase application resilience. For example, you'll see how to use the retry when and timeout operators to make the interaction between order service and catalog service more robust. Operators can perform actions on a publisher and return a new publisher without modifying the original one, so you can build functional and immutable data streams with ease. Project Reactor is the foundation of the Spring Reactive Stack, which lets you implement your business logic in terms of mono of T and flux of T. In the next section, you'll learn more about which options you have for building reactive applications with Spring. Section 8.1.3, Understanding the Spring Reactive Stack. When you build applications with Spring, you can choose between a servlet stack and a reactive stack. The servlet stack relies on synchronous, blocking I/O and uses the thread per request model to handle requests. On the other hand, the reactive stack relies on asynchronous, non-blocking I/O and uses the event loop model to handle requests. The servlet stack is based on the servlet API and a servlet container, such as Tomcat. In contrast, the reactive model is based on the Reactive Streams API, implemented by Project Reactor, and either Netty or a servlet container, version 3.1 as a minimum. Both stacks let you build RESTful applications using either classes annotated as REST controller, which you used in Chapter 3, or functional endpoints called router functions, which you'll learn about in Chapter 9. The servlet stack uses Spring MVC, while the reactive stack uses Spring Webflux. Figure 8.3 compares the two stacks. For a broader overview, you can refer to this link.
Figure 8.3. The servlet stack is based on the servlet API and supports synchronous and blocking operations. The reactive stack is based on Project Reactor and supports asynchronous and non-blocking operations.
Tomcat is the default choice for servlet-based applications like Catalog Service. Netty is the preferred choice for reactive applications, providing the best performance. All the major frameworks in the Spring ecosystem offer both non-reactive and a reactive options, including Spring Security, Spring Data, and Spring Cloud. Overall, the Spring Reactive Stack provides a higher-level interface for building reactive applications, relying on the familiar Spring projects without being concerned with the underlying implementation of the reactive streams.